Okay, if not, let's delve into the Schrodinger equation for the hydrogen atom. Okay, so one thing to note, which is interesting, is that it's a two-body system, right? And we haven't really done the Schrodinger equation for a two-body system yet, have we? I don't think so. So the Hamiltonian will have the kinetic energies for two particles, right? So we will have, say, P1 squared by 2m1 plus P2 squared by 2m2. And then the interaction energy or the potential energy between the two particles, which is, we know it's an inverse square law, and therefore it is a 1/r potential, right? So here we are using the CGS unit. How do we know it's a CGS unit? What would be the difference if it was an MKS unit? What else would I have to do?
One is kilogram meter, and CGS is a centimeter gram second.
Yeah, but would the equation look like this? What is the unit of charge in CGS called? Coulomb?
Yeah, I don't exactly remember.
Anyone else know the name of the? It's a memory test. It's a name of the or common knowledge test. Do you know the name of the unit of charge in the CGS unit? We know that Coulomb is the unit of charge in the MKS system. Anyone remember Coulomb's law?
There's some factor and q squared by,
yeah. And there's R12 squared, and there's R hat 12, and there's a K. Do you remember what K is?
It was the Coulomb constant, right?
Yeah, so it's called Coulomb constant, and it's a 1/4 pi epsilon naught, where epsilon naught is the
permeability of space, right?
permittivity.
Permittivity, right?
Permittivity of free space. Mu naught is the permeability.
Yeah, I always confuse these two.
Yeah, permittivity is for electricity, permeability is for magnetism. It's saying that, how easily can electric field lines, go through space, and permeability is like how easily can magnetic field, go through space. So if this were not in CGS units, what would be the difference in this equation? If we would have 1/4 pi epsilon naught here, right? And the unit of charge in CGS is called, Isa, do you know?
This one?
Right?
Yep.
Sir, is it
There's
the
a good reason why I'm
electrostatic
asking you.
unit?
Exactly, electrostatic Isu. That's why I asked Isa. It sounds
What?
was it Moon who said that, electrostatic unit? Or was it Wajihad? So, okay, it's electrostatic unit. Okay, so that's a
Is
CGS.
ESU the official one? Or is
Yeah, well, ESU. It's a short. It's like this is a mouthful, right? All right, so we have we have the Hamiltonian. So we now write down the Schrodinger equation. Well, the Schrodinger equation, we are going to write the time-independent Schrodinger equation, and that will be just H acting on psi, which will have x1 and x2. This is the first particle. It's let's call it proton. Is the proton's position, and this is the electron's position. And this will be minus h squared by 2m1 del 1 squared psi, big psi, minus h squared by 2m2 del 2 squared, big psi, minus e squared by r1 minus r2, big psi, and that will be equal to the total energy times psi, right? So this is the energy eigenvalue problem, which is our time-independent Schrodinger equation. So let me just start. Here, one is subscript refers to, say, proton. My handwriting today is not very good. And number two is particle is electron. Okay? So are we clear how to write down the Schrodinger equation of a multi-particle system?
Yes, sir.
Yeah. So if I were to give you, ask you to write down the Schrodinger equation n particle system, you would just say, okay, it's just something like n. So p goes from 1 to n. It's just pi squared by 2m acting on psi plus some potential which depends on all the particles, Okay? Any questions?
No, sir.
Okay, so